Hi everyone, in this video, we're going to present about gas refrigeration cycle, or specifically, Brayton refrigeration cycle. This is the list of all group members who involved in this presentation video.
Now, to give you some quick historical context, this whole idea started with George Brayton, a 19th century engineer. He originally designed what's called the Brayton cycle to generate power using gas. But engineers later found out that by reversing the process, they could actually use it for cooling. And that's how the Brayton refrigeration cycle came to be. It's especially useful in aviation because instead of using chemical refrigerants, it uses air, which is light, safe, and already available from the aircraft engines. Let's now go to the main components involved in cooling the aircraft cabin system step by step. The cycle starts by extracting hot, high-pressure air from the aircraft engines. This is called bleed air. This hot air is too warm to use directly, so it first enters a heat exchanger. Here, it's cooled down by outside air, also known as RAM air. This brings the temperature down a bit. Then comes the star of the system, the air cycle machines. It does three things. First, it compresses the air to increase both pressure and temperature. Second, it passes to heat exchanger 2, where the compressed air is cooled again using RAM air. Third, the air expands rapidly in the turbine, which causes a significant drop in temperature. This is where most of the cooling happens. After the air has cooled, some of the moisture inside it condenses. The water separator removes this to avoid fog or icing inside the cabin. Next, the cool dry air is mixed with some hot bypass air in the mixing chamber. Why? Because if we only use the super cold air, the cabin would be freezing. So this stage helps set a comfortable temperature. And finally, this conditioned air is distributed to the cabin, where it keeps passengers comfortable and maintain proper pressure.
Hi, my name is Yusop, and my part is about the basic working principle of the gas refrigeration cycle. And they also can call as the Brayton refrigeration cycle. And what is the Brayton refrigeration cycle? This is a thermodynamic cycle used for cooling where the gas, such as air, serves as the working point. It operates similarly to the Brayton power cycle but in reverse. It will extracting heat from low temperature source and rejecting it to the high temperature sink. And for the Brayton power cycle, it will extracting heat from high temperature source and rejecting it to the low temperature sink. So why we say that gas refrigeration cycle is similar to the Brayton power cycle. And now we can look at the diagram on the left side. It has shown that the following cycle processes for the gas refrigeration cycle. First is about the compressing the gas. It will increase its pressure and temperature. Second is cooling the compressed gas. It's rejecting heat to the surrounding. Third is expanding the gas, lowering its temperature below the refrigeration temperature. And final is absorbing heat from the space to be cooled. It's called as refrigeration effect. Next, this will be the more detail about the four main process of the gas refrigeration cycle. First is the isotropic compressors. What is the isotropic? Means that the entropy of the first state of gas is equal to the entropy of the final state of the gas. In simple way, is delta S is equal to 0, and at this process is adiabatic process. And in this process, a compressor increases the pressure and temperature of the gas. And what input is required, right? We must make sure that the compressor can be operated. Second is about the isobaric heat rejection. What is the isobaric? Means that the pressure of the first state of gas is equal to the pressure of the final gas of the gas. Means delta P is equal to 0. And in this process, the high pressure, high temperature gas passes to a heat exchanger. Heat is rejected to the surroundings, and the temperature decreases while pressure remains constant. And third is isotropic expansion. And isotropic, I have mentioned before, that means the entropy remains constant, delta S equals to 0. And in this process, the gas expands in the turbine and doing a work. The pressure and temperature drop significantly. And last process is the isobaric heat absorption. The cool, low pressure gas absorbs heat from the refrigerated space, and the temperature rises while pressure remains constant, and the cycle will be repeated. And this cycle is paused the same as the same gas is refrigerated in most applications. So open cycle like aircraft cooling also as.
So why is air selected as the working fluid in this refrigeration cycle? First of all, air is naturally available and cost efficient. Air is abundant and does not need special storage or refilling. That means no cost for the working fluid itself, unlike other refrigerants, which can be expensive. Next, air is safe and environmentally friendly. Air is non-toxic, non-flammable and inert to operation. Air has zero ozone depletion potential, ODP, and zero global warming potential, GWP, which means zero impact to environment. Many other refrigerants have high GWP and ODP, which can contribute to ozone depletion and global warming. Air can also reduce the system complexity. This is because air remains a gas during or throughout the cycle, eliminating the need for evaporators, condensers, and complex pressure controls. Furthermore, air can be easily compressed and expanded, which makes the cycle efficient and simple in small or middle-scale cooling system. Lastly, air has long-term stability and does not undergo chemical degradation during compression and expansion. That means there is no concerns in refrigerant leakage and no requirements in special handling procedures. Other refrigerants can break down over time, especially in high temperatures, leading to system wear. This side-by-side table sums it up. Air wins over other refrigerants on availability, safety, environmental impact, and chemical degradation. These properties of air make it ideal to be used as the working fluid in the refrigeration cycle. Now, how does the air cycle actually work? From point 1 to 2, isentropic compression takes place. The cold air from the refrigerator is drawn into the compressor and compressed isentropically. The pressure and temperature increases while the volume decreases. Entropy stays constant during this process. There is no heat absorbed or rejected by the air. Next, constant pressure cooling process takes place from point 2 to point 3. The warm air from the compressor is then passed into the cooler, where it is cooled at constant pressure. The temperature and volume reduces, while pressure remains constant. Heat rejected by the air is given by heat capacity times the change in temperature between T2 and T3. From point 3 to point 4, isentropic expansion is involved. Air from the cooler is presently thrown into an expander and is expanded isentropically. The pressure and temperature decreases while the volume increases. Entropy stays steady during this process and no heat transfer takes place. Constant pressure expansion takes place from point 4 to point 1. The cold air from the expander is then passed into the refrigerator and expanded at a constant pressure. The volume and the temperature increases while the pressure remains constant. Heat absorbed by the air is given by heat capacity times the change in temperature between T1 and T4. I'll explain about how can we derive the equation for the coefficient of performance or COP in this gas refrigeration cycle. First, we define COP as the ratio of heat absorbed to the work done. COP is equal to heat absorbed divided by work done. From the first slide, we know the heat absorbed during the cycle per kg of air is Q in is equal to Cp times T1 minus T4. The heat rejected is Q out is equal to Cp times T2 minus T3. So work done per kg of air is W net is equal to Q out minus Q in is equal to Cp times T2 minus T3 minus T1 minus T4. Substitute this into the COP formula. We get COP is equal to Cp times T1 minus T4 divided by Cp times T2 minus T3 minus T1 minus T4. This simplifies to COP is equal to T1 minus T4 divided by T2 minus T3 minus T1 minus T4. Next, we apply the isentropic relations to express temperatures in terms of pressure ratios. For process 1 to 2, T2 divided by T1 is equal to P2 divided by P1 times to the power of gamma minus 1 over gamma. And for 3 to 4, T3 divided by T4 is equal to P3 divided by P4 to the power of gamma minus 1 divided by gamma. Using this, we get another COP formula. COP is equal to 1 divided by P3 divided by P4 to the power of gamma minus 1 divided by gamma minus 1. Finally, we introduce the compression ratio, RP, which is equal to P2 divided by P1 is equal to P3 divided by P4. So the COP becomes COP is equal to 1 over RP to the power of gamma minus 1 over gamma minus 1. This final form clearly shows how COP depends on the pressure ratio and specific heat ratio gamma. A lower pressure ratio means a higher COP, which means better performance.
We move to the benefit of the gas refrigeration cycle. Okay, so first, it uses a simple working fluid. Usually, it is a single gas like air, nitrogen, or helium. These gases are non-toxic and safe to use, especially in enclosed environment like aircraft cabins or space system. Second, there is no phase change in the system. This means the gas stays in the same state. There are no condensation or evaporation, so the system needs fewer components, making it easier to build and maintain. Next, the system is lightweight. Since it doesn't need large condensers or evaporators, the design is simpler and more compact. It also doesn't require large tanks like vapor system, which help reduce the overall weight. And finally, it has a fast cooling response. Gas-to-gas heat exchangers can react very quickly, especially at high flow rates, so you can get the immediate cooling effect with a very little delay. In short, the gas refrigeration cycle is simple, safe, lightweight, and fast, making it a great choice in many specialized applications. So now, let's look at the limitation of the gas refrigeration cycle. First, gas refrigeration systems use complex mechanical components such as fast rotating turbine and compressors. This component needs precise design, making the system more technically demanding and expensive to build. Second, they have a low coefficient of performance, which is COP. This means the system is not very efficient. Compressing air to gas to high pressure needs a lot of energy, and to get the same cooling effect, the heat exchangers have to be larger. Third, the system has high maintenance demand because of the many moving mechanical parts, especially the rotating ones. Regular service is required to keep everything working properly. Lastly, gas refrigeration system need a large equipment size. This is because gases have lower density compared to liquid, so we need bigger compressors, turbine, and heat exchangers to achieve the same cooling effect. So overall, while gas refrigeration has its advantage, this limitation make it less suitable for certain applications. So this is a summary of advantage and disadvantage of gas refrigeration cycle. Now let's look at some important application of the gas refrigeration cycle in real world industries. First, we have the aircraft air cycle machine, which is ACM. These systems are commonly used in both commercial and military aircraft, including those operating in Malaysia. ACM serves as an environmental control system in precious aircraft that use gas turbines. They help regulate the temperature and pressure inside the aircraft cabin, ensuring comfort and safety for passengers at high altitude. What makes the system efficient is that the use of aircraft own compressed air, which is expanded and cooled through the gas refrigeration cycle to produce cold air in the cabin. So the second is, we have application in the liquefaction of LNG, which is liquefied natural gas, and other cold flow processes. In this case, the gas refrigeration cycle is used to cool natural gas down to 162 degrees Celsius, transforming it into a liquid. Liquefying the gas significantly reduces its volume. This is very important for storage and transportation purposes. It allows natural gas to be shipped more easily and economically, especially over long distance. This process is widely used in the energy industry around the world. So, even though the gas refrigeration cycle has its limitation, it plays a crucial role in key sectors like aviation and energy.
Recent developments in gas refrigeration cycles. The first one is integration with modern jet engines. Modern jet engines now incorporate advanced air cycle machines, ACMs, as part of the environmental control systems, ECS. These systems operate based on Brayton cycle principles using bleed air from the engine, which is expanded through turbines to produce cooling. This integration enhances specific cooling capacity, reduces parasitic power loss, and eliminates the need for chemical refrigerants, optimizing both energy efficiency and system mass. What this slide talks about is how gas refrigeration cycles are now used in modern aircrafts. The systems called ACMs use bleed air from the engine and cool it down using principles of the Brayton cycle. The thing here is they don't rely on chemical refrigerants like normal air conditioning units do. Instead, they use the engine's own airflow, making it lighter, more efficient, and eco-friendly. For the second one, the adoption of advanced composite materials, the use of fiber-reinforced polymers, FRPs, and ceramic matrix composites, CMCs, in heat exchangers, in turbines and compressors significantly improves the thermomechanical performance of gas refrigeration systems. These materials provide high thermal resistance, low density, and corrosion resistance, which are critical in maintaining isentropic efficiency and minimizing irreversibility due to heat transfer losses. Now, for the material used in these systems, this slide focuses on advanced materials like fiber, reinforced polymers, and ceramics. That these materials are essential because they resist heat and corrosion, and they're lightweight. That means the system doesn't just cool efficiently, it also doesn't add much weight to the aircraft. The diagram shows a recuperator, a type of heat exchanger made using materials. It's designed to minimize energy loss and improve thermal efficiency. For the third slide now, we're going to talk about the expansion to extraterrestrial and UAV application, essentially space aeronautics stuff. Gas refrigeration cycles are increasingly utilized in spacecraft, thermal regulation, and high-altitude unmanned aerial vehicles, UAVs, due to their independence from gravitational orientation and liquid phase transitions. Their performance remains stable under low-pressure conditions where traditional vapor compression system would fail, making them ideal for thermal vacuum environments. What it's saying is that gas refrigeration isn't just for planes. Essentially, it's also used in spacecraft and high-altitude drones. The reason being, these systems don't rely on gravity or liquids to work, so they're perfect for outer space and for very high altitude, for very high altitudes where traditional cooling systems fail. This diagram illustrates heat absorption and rejection in a satellite, where gas refrigeration keeps internal system cool despite extreme conditions outside. Now for the fourth one, automation and intelligent control systems. Integration of real-time feedback control using PID algorithms and machine learning-based predictive maintenance enables dynamic regulation of mass flow rates, turbine inlet temperatures, and pressure ratios. These systems optimize isentropic efficiency, reduce manual calibration, and extend system lifetime by minimizing entropy generation and component fatigue. So these, essentially what's saying is that these modern systems also include smart controls. They use feedback loops and AI prediction to automatically adjust how the system runs. That means fewer errors, better performance, and less maintenance. By fine-tuning these variables like mass flow and pressure, the system runs more efficiently and lasts longer. Now, for the conclusion, the gas refrigeration cycle, derived from the reverse Brayton cycle, offers a lightweight, environmentally friendly, and mechanically simple solution for cooling applications, especially in aviation, by using air as a working fluid. The system avoids harmful refrigerants, ensuring zero ODP and GW impact. The cycle involves isentropic compression and expansion alongside with isobaric heat rejection and absorption, and is well represented on PV&TS diagrams. Despite a relatively low coefficient of performance COP compared to the vapor compression systems, its compactness, fast thermal response, and suitability for open systems make it ideal for aircraft cabin cooling and LNG applications. Recent technological developments, including integration with jet engines, use of composite materials, and regenerative configurations, and intelligent control system, have further improved system efficiency and reliability. Additionally, the expansion of gas refrigeration into spacecraft and UAVs highlights its adaptability in extreme environments. Overall, the gas refrigeration cycle remains a relevant and evolving solution for high-performance thermal management in both terrestrial and aerospace systems.
And that's all for now. Hope you enjoy watching this video.